Every news outlet covered this earthquake. Almost none of them covered the part that actually has scientists worried. And the part they missed isn't complicated. It's just inconvenient. On April 20th, 2026, a magnitude 7.7 earthquake struck off the coast of northeastern Japan. Every major outlet ran the same story: powerful quake, tsunami warning, nearly 176,000 people evacuated. Waves reached 80 centimeters, no major damage. Advisory issued, move on. What those stories didn't tell you is that seismologists had been watching this exact segment of fault since 2011, that a warning shot arrived 3 weeks before April 20th, and nobody connected it publicly, that the government agency monitoring this fault then did something it has done exactly 3 times in recorded history, and that, as of right now, that same agency cannot tell you whether April 20th was the disaster or the rehearsal. Stay with me until the end of this video, because what all of this adds up to is something the seismology community is only beginning to say out loud. And the part they're most reluctant to say is the part that affects you directly. Even if you live in Oregon, even if you live in Washington State, even if you've never thought about Japan's fault system in your life, if this has you hooked, subscribe to Stellar so you don't miss what comes next. Because this story is just getting started. Drop a comment below. I want to know where in the world you're watching from, what time it is where you are, and your honest take on this. Was April 20th the main event? Or was it the opening act? Tell me what you think. Now, settle in because we've got a lot to unpack. Part 1. What the news told you and what it left out. Let's start with what every outlet got right. April the 20th, 2026, 4:53 in the afternoon, local time. A magnitude 7.7 earthquake struck the seafloor of the Pacific Ocean, approximately 100 kilometers off the coast of Iwate Prefecture, in northeastern Japan. Depth, 20 kilometers. The shaking was felt as far south as Tokyo, where buildings swayed for several minutes. The Japan Meteorological Agency issued a tsunami warning within minutes. Waves of up to 3 meters were forecast. 175,957 people across 13 cities, 21 towns, and 6 villages in 5 prefectures received evacuation orders. Japan's extraordinary early warning infrastructure activated exactly as designed. The maximum wave that arrived measured 80 centimeters of Kuji Port in Iwate, and 10 people were injured, 2 seriously. 39 buildings damaged in Aomori Prefecture, a road damaged in Ishinomaki. Roughly 200 households lost power in Hiraizumi. No abnormalities reported at Fukushima Daiichi or Daini. No radiation changes. By any reasonable measure of physical destruction, a non-event. That is a story every outlet told, and it is accurate, all of it. Here is the part that is also accurate, and that almost nobody told. The USGS initially measured this earthquake at magnitude 7.4. The Japan Meteorological Agency later revised it upward to 7.7. That gap matters. On the Richter scale, every full unit represents roughly 32 times more energy released. The gap between 7.4 and 7.7 is not a minor correction. It represents nearly 3 times more energy than the initial measurement suggested, and upward revisions of this kind from a body with Japan's monitoring density typically indicate one of 2 things: a rupture larger than initial waveforms captured, or a rupture slower than expected, releasing energy over a longer duration in a way that arrives late in the seismic record. Slower ruptures are not reassuring. They are often associated with fault segments that slip in complex, distributed ways rather than clean, rapid breaks. Complex, distributed slip has implications for what the fault still has stored. And then, the JMA did something it has done exactly 3 times in the history of the protocol. It issued a subsequent earthquake advisory. Not an aftershock warning, not a standard precautionary notice, a specific, named, the legally defined advisory protocol that was created for one reason and one reason only. Because post-2011 science revealed that large earthquakes on this fault system can trigger even larger ones, and that the window in which that happens can be days, not hours. That advisory covered 182 municipalities across 7 prefectures, from Hokkaido in the north to Chiba Prefecture on the outskirts of Tokyo in the south. Tens of millions of people. The news told you an advisory was issued. What the news did not tell you is what the advisory's existence actually means. And that is where this story begins. Part 2. The advisory the news explained wrong. Most outlets reported the 1% figure, then moved on. Let me tell you what that number actually means. And the baseline probability of a magnitude 8 or stronger earthquake along the Japan Trench and Kuril-Kamchatka Trench on any given week is 0.1%, not 0, but vanishingly small by any practical measure of daily risk. It is background noise. It is the number that exists in every week of every year, reflecting the accumulated stress of a plate boundary that moves 7 to 9 centimeters per year. After April 20th, the JMA raised that figure to 1% for the following 7 days. That is a 10-fold increase. Here is the number that needs context. If you were told that the probability of a fatal crash on the flight you're about to board had increased by a factor of 10, that plane does not take off. Not because 1% is a certainty, but because a 10-fold increase in probability on a catastrophic outcome represents a qualitative change in the risk environment, not a quantitative footnote. The advisory is not a prediction. The JMA was explicit about this, and clear about why. Seismology as a science does not currently have the tools to predict earthquakes. What it has are probability assessments, and what it can do is acknowledge, institutionally and publicly, that the probability environment has changed. Here is what the advisory actually is. It is the Japanese government saying, in the clearest language a government agency can use without causing mass panic, we do not know if the worst is over. The earthquake that just happened may have released the stress that was stored in this fault segment, or it may have transferred that stress to adjacent segments. We cannot tell you which. And for the next 7 days, the probability that we will find out the hard way is 10 times higher than it was yesterday. That is what 1% means in this context, not a small number, an alarm. Now, this protocol did not exist before 2022. It was created specifically because post-2011 research revealed something that the seismology community had not fully appreciated before the Tohoku disaster. Large subduction zone earthquakes do not simply release stored stress. They redistribute it. One fault segment failing can push stress onto adjacent segments, loading them closer to failure rather than relieving the system. The advisory was designed to acknowledge that reality institutionally, and here is the fact that appeared in zero mainstream news coverage of the April 20th event, that this is the 3rd time this protocol has ever been issued. Not the 3rd time ever in Japan's history of the earthquake monitoring, the 3rd time since the protocol was created in 2022. 3 activations of a newly created emergency advisory mechanism in roughly 18 months on the same fault system. The first in 2024, the second in December 2025, following a magnitude 7.5 off Iwate Prefecture. And now, April 2026. 3 activations, same fault, 18 months. That pattern is not in any mainstream coverage, and that pattern is the beginning of the story this video is actually telling. Part 3. The foreshock. Nobody reported March 27th, 2026, 3 weeks before April 20th. A magnitude 6.5 earthquake struck the Iwate segment of the Japan Trench, almost exactly the same location as the April 20th event. It produced coastal shaking, no significant tsunami, a brief mention in a handful of seismology-focused outlets, and then silence. Within 24 hours, it was gone from the news cycle entirely. It should not have been forgotten. Here is the physics of what happened between March 27th and April 20th. A 7.7 releases more than 40 times the energy of a 6.5. Not a little more, 40 times. That is not incremental escalation. That is a magnitude shift. And it occurred on the same fault segment, in the same location, within 3 weeks. To understand why that matters, you need to understand what a foreshock is and what it isn't. A foreshock is an earthquake that precedes a larger earthquake on the same fault. That definition sounds simple. It is not, because a foreshock is only identifiable in retrospect, in real time, in the days and weeks after a 6.5 strikes a fault segment. It is indistinguishable from a main shock. It looks identical on every instrument. The seismograms are the same. The focal mechanisms are the same. The aftershock sequences that follow it are the same. There is no measurement available to any seismologist on Earth that will tell them, in real time, whether a given earthquake is the main event or the opening act of something larger. That number needs context. Historically, roughly 5 to 10% of significant earthquakes are later identified as foreshocks. On most fault segments, that probability is low enough that treating every event as a potential foreshock would generate continuous public alarm with little practical benefit. But this is not most fault segments. This is the Iwate segment of the Japan Trench, or the segment that post-2011 scientific literature specifically flagged as a region of elevated concern. The segment where stress had been accumulating for 15 years on top of changes produced by the Tohoku disaster itself. The segment that had just produced a magnitude 6.5 3 weeks earlier. And the channel in this space that your audience watches most closely, Project Nightwatch, flagged the March 27th event when it happened. They told their audience to watch this segment, to pay attention, to note the location and the stress history. Nobody in mainstream media made that connection. Nobody asked the question publicly that the data was already raising. If the March 27th event was the foreshock to April 20th, what is April 20th? Part 4. The 15-year warning in the scientific literature. This is the part of the story that has seismologists genuinely on edge. April the 20th didn't come out of nowhere. It came from exactly where the science said to watch. After the March 11th, 2011 Tohoku earthquake, the magnitude 9.0 disaster that killed nearly 20,000 people, destroyed Fukushima, and permanently changed how Japan thinks about seismic risk. The scientific community spent years mapping what that rupture had done to the rest of the fault system. The question they were asking was not simple. A magnitude 9.0 rupture releases an extraordinary amount of stored energy. Common sense would suggest that a rupture of that scale relieves stress across the entire fault system, that the surrounding segments are safer afterward, not more dangerous. The science found the opposite. The large sections of the Japan Trench megathrust were brought closer to failure by the Tohoku rupture, not further from it. This is the phenomenon of Coulomb stress transfer. When one fault patch fails, the stress it was carrying does not disappear. It redistributes. It flows outward through the rock to neighboring fault patches. Sometimes that transfer loads those patches closer to failure. Sometimes it stabilizes them. The direction depends on the geometry of the fault, the pattern of slip, and the orientation of the receiving segment. 2 peer-reviewed studies documented this directly. A 2011 paper by Toda and colleagues published in Earth, Planets and Space, and later summarized by the USGS, examined Coulomb stress changes across the Japan Trench following Tohoku, and they found that large sections of the megathrust were brought closer to failure. That the northern segments in particular, including the region off Iwate, received positive Coulomb stress changes, stress added, not relieved. A second study by Sato, Hiratsuka, and Mori, also published in Earth, Planets and Space, examined Coulomb stress changes for fault aftershocks near the Japan Trench, specifically triggered by the 2011 event. They found the stress changes strongly dependent on the shallow slip near the trench. The region off Iwate was in the zone of elevated positive stress change, and a 2017 study in Scientific Reports confirmed this from underground. Researchers measured actual stress levels in the Kamaishi mine in Iwate Prefecture, located near the northern termination of the Tohoku rupture. The measurements, as taken before and after the 2011 earthquake, showed that principal stresses in the rock more than doubled after the main shock. More than doubled, at a location in the same geographic zone as the April 20th epicenter. Here is the part that should stop you cold. Those studies were not obscure. They were peer-reviewed, published, cited, and available to anyone following the seismology literature in the years after 2011. The warning they collectively represented was not a prediction. It was not a specific forecast of a specific earthquake at a specific time. But it was a clear, documented, scientifically grounded identification of the Iwate segment as a region of elevated concern, a region where the 2011 disaster had loaded stress rather than removed it. That segment remained quiet from 2011 until March 27, 2026. 15 years, and accumulating. And then in 3 weeks, it produced a 6.5, followed by a 7.7. The science said to watch this area. The science was right. And the question it cannot yet answer is whether the watching is over. Part 5. What seismology cannot tell you. This is the part most news coverage avoids, because it is uncomfortable, and because it is the most honest thing that can be said about where the science currently stands. Seismology cannot tell you in real time whether a major earthquake was the main event or the foreshock. Not because of a gap in monitoring. Japan has the most sophisticated seismic monitoring network on Earth. Not because of a gap in computing power or modeling capability. Not because of a lack of data. Because the physics of fault rupture does not, at the point of rupture, carry information about whether a larger rupture will follow. The fault does not announce its intentions. A foreshock is a main shock that is later reclassified. That reclassification requires the larger earthquake to occur. Before that larger earthquake, every instrument and every model treats the preceding event as a main shock, because for all observable purposes, it is one. Historically, 5 to 10% of significant earthquakes are later identified as foreshocks. That means that for every earthquake like April 20th, in the hours and days immediately following, there is a real and non-trivial probability that the sequence is not finished. Not a certainty, a probability. And on this particular fault segment, with this particular stress history, with the specific pattern of stress loading documented in the scientific literature since 2011. That probability is harder to calculate than average. The baseline is elevated. The context is not typical. The advisory system was designed precisely to acknowledge this, to say, in institutional language, what the science actually knows and doesn't know. The JMA does not issue that advisory unless the post-event probability assessment has shifted in a meaningful way. The fact that it was issued for the third time in 18 months on the same fault system is not routine. It is the scientific community's clearest available signal that something in this fault system is in the state of activity that warrants sustained attention. And then the advisory was lifted. At exactly 5 p.m. on April the 27th, the Cabinet Office official Kota Iwamura stood at a press conference and said the following: "The lifting of the advisory doesn't mean that a major earthquake will no longer occur. Not a reassurance, a reminder. The 7-day elevated probability window closed. The underlying stress state of the fault did not. And on the same day, the advisory was lifted. A magnitude 6.2 earthquake struck Hokkaido. No tsunami alert, no new advisory. But the seismometers did not stop recording. They never do. What scientists are watching now, the aftershock rate and its decay pattern following April 20th. Whether it follows the expected Omori law decay or shows anomalies suggesting continued fault activity. GPS crustal displacement data from Japan's Geospatial Information Authority are watching for any slow slip signals on adjacent segments that would indicate continued stress transfer along the trench, and the background seismicity rate across the northern Japan trench system, looking for any clustering that would indicate stress concentrating in a new location. Those measurements are being taken, right now, every day. The results are not in yet. And that is the honest answer to the question the news cycle moved on from before it was ever asked. Part 6. The Cascadia Mirror. Now let me tell you why this matters to you specifically. Even if you are watching this from Oregon, from Washington State, from Northern California, from anywhere in the Pacific Northwest, the Cascadia subduction zone. It runs offshore from Cape Mendocino in Northern California north to Vancouver Island in British Columbia, and roughly 1,130 kilometers of fault. The same basic mechanism as the Japan Trench. One tectonic plate subducting beneath another, accumulating stress at the plate boundary until the locked interface fails catastrophically. The Japan Trench and the Cascadia subduction zone are geologically analogous systems. Same mechanism, same type of fault, same physics of stress accumulation and eventual release. The Japan Trench is, in the most literal scientific sense, the closest working model the world has for understanding what Cascadia will eventually do. Here is the critical difference. The Iwate segment of the Japan Trench had been accumulating stress since 2011, 15 years. That 15 years of accumulation produced the sequence you have spent the last hour hearing about. A foreshock, a 7.7, 3 advisory activations, and 15 years of scientific literature saying, watch this area. The Cascadia subduction zone last ruptured in January 1700. That date is known with precision because Japanese coastal villages recorded an orphan tsunami, a tsunami with no locally felt earthquake, that arrived from across the Pacific on the night of January 27, 1700. Scientists traced it backward to its source, a full margin Cascadia rupture off the Pacific Northwest coast. That was 326 years ago, not 15 years of accumulation, 326 years. FEMA has run the numbers on what a full Cascadia rupture produces today. The agency calls it the worst natural disaster in American history, Their estimates: 13,000 fatalities, 27,000 injuries, 620,000 buildings collapsed or destroyed. That includes approximately 100 hospitals and 2,000 schools, and more than 1 million people displaced. Another 2.5 million in need of food and water. Economic losses exceeding $30 billion. Tsunami waves reaching 100 feet in some locations, arriving at the coast within 15 to 35 minutes of the earthquake. That number needs context. The shaking from a full Cascadia rupture would last 4 to 6 minutes, not the 20 to 30 seconds of a typical large earthquake. 4 to 6 minutes of ground motion intense enough to collapse unreinforced masonry buildings, liquefy low-lying ground in coastal areas, trigger landslides across the coast range, and damage or destroy bridges and overpasses across the region. And then the tsunami arrives. Here is what Oregon's own emergency management officials say about preparedness for this event. In their own words, Representative David Gomberg, in whose district covers the Oregon coast, "I think that Oregon is certainly not as well prepared as they could be here at the coast." Lincoln County planning official Onno Husing: "We will have islands, the routes to the valley. Everybody talks about getting people out of here, because a lot of these highways, when Cascadia rips out, it's going to devastate the I-5 corridor as well." Representative Paul Evans, who has been trying to pass a $300 million disaster preparedness package through the Oregon legislature, described the 2026 session as the last stand. The emergency alert system during a July 2025 tsunami warning on the Oregon coast only reached people who had pre-registered with the state system. Not every cell phone in the impact zone. People visiting from out of town, in some cases, received no alert at all. The Oregon Department of Emergency Management doesn't recommend 72 hours of supplies for a Cascadia event. They recommend 2 weeks, because they know infrastructure will be disrupted for months, not days. And the federal capacity that would normally supplement state response is being cut. The Trump administration announced in 2026 it is moving toward eliminating FEMA entirely by December. Representative Evans: "We're going to be on our own for a longer period of time, and we need to be prepared for that." Here is the part that most coverage misses entirely. Japan is not a warning from the other side of the world. Japan is the working demonstration of what a fault system looks like in the years before a major rupture. The stress patterns, the escalating advisory activations, the foreshocks that only become foreshocks in retrospect, at the scientific literature pointing at specific segments, the gap between what the science knows and what the public understands. All of that is happening on the Japan Trench right now, and the Cascadia subduction zone is 326 years further along the same trajectory. Part 7. What April 20th actually resolved. Let's be precise about what we know. April 20th produced 10 injuries, 2 serious, 39 damaged buildings, 80 centimeters of water at Kuji Port. By any measure of physical destruction, a near miss. A demonstration that Japan's post-2011 investment in early warning infrastructure, coastal barriers, and public preparedness works. That is real. That is worth acknowledging directly. But here is what April 20th did not resolve. It did not resolve the question of whether the Iwate segment has fully released the stress that has been loading it since 2011. A 7.7 is a large earthquake. It is not a megathrust event. The Japan Trench is capable of producing magnitude 9.0 ruptures. The 2011 Tohoku earthquake was a 9.0. The 869 Sanriku earthquake, which struck the same coastal region over 1,100 years ago, is estimated at magnitude 8.6 to 9.0. The fault system that produced both of those events has not changed. The convergence rate of 7 to 9 centimeters per year has not changed. The stress accumulation mechanism has not changed. A 7.7 releases enormous energy. On the logarithmic scale, a 9.0 releases roughly 180 times more energy than a 7.7. 180 times. If the Iwate segment was loaded toward a 9.0 class rupture, over 15 years of stress accumulation following Coulomb transfer from Tohoku, a 7.7 does not necessarily empty that account. It may have made a significant withdrawal, or it may have transferred stress laterally to adjacent segments, or both. And the GPS displacement data from Japan's Geospatial Information Authority will tell that story over the coming months. The aftershock sequence will contribute to that picture. The slow slip monitoring on adjacent segments will add more. Not a clear answer. A picture being assembled in real time by instruments that are working on it right now. Here is the part that most post-event coverage misses entirely. The Iwate segment has now produced 3 sequences in approximately 18 months that each triggered the subsequent earthquake advisory. That pattern has no precedent in the short history of the protocol. It can mean one of two things. Either the fault is releasing accumulated stress in a series of managed, incrementally smaller events that are gradually reducing the hazard, nor it is in a period of heightened instability in which each event is redistributing stress to adjacent segments and sustaining the elevated risk environment. Those two interpretations produce opposite conclusions about what comes next. And seismology, right now, cannot definitively tell you which is correct. The advisory is gone. The cameras have left. The news cycle is already on the next story. The seismometers have not moved. Part 8. What 1,100 years of history says, the Japan Trench does not operate on a human news cycle. It operates on geological time, and there is more recorded history of this fault's behavior than almost any subduction zone on Earth. The 869 Sanriku earthquake. It struck in July of 869 AD. The historical record describes it as producing a massive tsunami that inundated the Sendai Plain, killing thousands. A modern analysis of sediment deposits from that event places its magnitude at 8.6 to 9.0. The tsunami deposits extend kilometers inland in the same coastal region that was inundated by the 2011 event. Same fall, same mechanism, same geography. That sequence continued. The 1611 Keicho Sanriku earthquake, the 1896 Meiji Sanriku earthquake, which killed over 22,000 people with a tsunami that generated almost no warning shaking. The 1933 Sanriku earthquake, magnitude 8.4, which struck within the subducting plate rather than at the plate interface, and then 2011. The Wikipedia article on the 2026 Sanriku earthquake notes that the plate boundary in the area of the April 20th epicenter shows an abrupt increase in dip from about 5 degrees to about 15 degrees, approximately 80 kilometers landward of the Japan Trench. And this structural feature, this geometry of the fault, is one reason this specific segment produces such complex rupture patterns. The changing dip angle affects how stress distributes across the fault surface during and after rupture events. Here is the part that should stop you cold. The 1,100-year record of this fault system shows that it produces major ruptures on timescales of decades to centuries, not once, repeatedly. The same coastal communities, the same inundation zones, the same fault patches, generation after generation of people rebuilding, in the same locations, knowing what happened before, and sometimes not knowing, and the fault rupturing again regardless. That number needs context. The gap between the 869 earthquake and the 2011 earthquake was 1,142 years. That is not a safe gap. That is the time it takes for cultural memory to erode completely, for the people living on the coast to lose the institutional knowledge of what the water can do, for the infrastructure to be built in the inundation zone because no one alive has seen the inundation zone activated. The stone markers placed along the Sanriku coast by survivors of previous tsunamis, saying, "Do not build below this line," were in some cases ignored by subsequent generations who could not viscerally connect with an event that happened before their grandparents were born. After 2011, Japan spent billions on concrete seawalls, on elevated evacuation roads, on tsunami-resistant building codes, on public education programs that now teach children from primary school what to do when the ground shakes, that the April 20th evacuation of 175,957 people was orderly. The casualty count of 10 injured was extraordinarily low for an earthquake and tsunami warning of this magnitude. That outcome was earned by 15 years of investment, by a culture of preparedness built on the explicit memory of catastrophe. The Cascadia subduction zone's last rupture was 326 years ago. The Pacific Northwest has no institutional memory of it. No living generation has experienced it. The stone markers, the cultural transmission of the danger, do not exist in the same way. What exists instead are FEMA impact models, state emergency management officials testifying that Oregon is not as prepared as it needs to be, and a federal emergency management agency that may not exist in its current form by the end of 2026. In Part 9, what the aftershock data is and isn't saying. In the days following a major earthquake, seismologists watch the aftershock sequence the way a doctor watches a patient's vital signs after surgery. The pattern tells you something about the state of the system. Not everything, something. Aftershocks follow a predictable mathematical pattern called Omori's law, named for Japanese seismologist Fusakachi Omori, who first described it in 1894. The rate of aftershocks decreases over time in a specific way, rapid at first, then declining, then tapering off toward the background level. A sequence that follows Omori's law cleanly is generally consistent with a main shock that has done its work and left the fault in a state of gradual stress relaxation. A sequence that deviates from Omori's law, yet that shows an anomalous rate increase partway through, or that produces aftershocks unusually large relative to the main shock, is more concerning. Not definitively alarming, but worth watching more closely. The aftershock sequence following April 20th is being monitored by Japan's National Research Institute for Earth Science and Disaster Resilience, by USGS, and by academic seismology groups globally. The results are being updated in real time. The data is not yet resolved into a clear narrative. Here is what is confirmed. On April 27th, the same day the advisory was lifted, a magnitude 6.2 earthquake struck Hokkaido. The Japan Times confirmed it. No tsunami alert, no new advisory, but it is documented. A 6.2 on the day the elevated probability window formally closed. That event does not, by itself, indicate the sequence is continuing in an alarming direction. A 6.2 following a 7.7 is within the expected aftershock magnitude range for this type of event. What it does indicate is that the fault system remains active, that the seismometers are still recording events, that the ground has not returned to the background state it was in before March 27th. That number needs context. The Japanese Geospatial Information Authority's GPS network is one of the densest crustal deformation monitoring systems on Earth. More than 1,300 continuously operating GPS stations across Japan. These instruments measure millimeter-scale ground movement. They are watching right now for any signal that the crust adjacent to the April 20th rupture zone is deforming in ways that suggest continued loading or stress transfer, a slow slip event on an adjacent segment, a gradual aseismic movement of the fault that doesn't produce ground shaking but does shift the stress environment, would show up in this data before any seismic signature appeared. Those measurements take weeks to months to interpret meaningfully, the picture being assembled from GPS data, aftershock sequences, and the broader seismic record will tell a more complete story of what April 20th did to the stress state of the Japan Trench. That story is not finished. It is being written now, in data that updates daily, in instruments that never sleep, by scientists who are asking the same question the advisory was designed to acknowledge. Was that the main event? Or was it the transfer? Part 10. The infrastructure question Japan answered. After 2011, Japan made a choice. The choice was not cheap, it was not fast, and it was not guaranteed to work. But it was made clearly and collectively and funded seriously. Japan built seawalls. Some of them are 15 meters tall, running for hundreds of kilometers along the Sanriku coast, massive concrete structures visible from the sea. In some coastal towns, the walls are so large they block the ocean view entirely. There are communities on the Sanriku coast where you can stand in the town center and not see the water that is 200 meters away. The wall is between you and the ocean. Japan redesigned its tsunami evacuation infrastructure. Elevated roads built specifically for evacuation. Signage updated. Evacuation tower structures in communities where there is no natural high ground nearby. Tsunami drill participation embedded into school curricula and workplace emergency planning. Japan rebuilt and expanded its early warning network, the system that gave coastal residents time to evacuate on April 20th, sending warnings to millions of phones in the seconds after the seismic waves were detected, is the product of post-2011 investment in sensor density, processing speed, and alert infrastructure. And Japan maintained a culture of active memory. The date of the 2011 earthquake, March 11th, is observed as a day of national remembrance. The stories of the wave are taught. The inundation maps are public. The evacuation routes are marked. The seawalls are there every day as a physical reminder of what the water can do. The result on April 20th was 10 injuries and 80 centimeters of water, against a tsunami warning of 3 meters, against a 7.7 earthquake, against 175,957 people who had to move. That outcome is not luck. That is 15 years of work. Here is the part that keeps me up at night about what comes next. The Cascadia subduction zone faces the same eventual rupture, with a fraction of Japan's post-disaster institutional infrastructure. A warning system that did not reach all phones during the July 2025 test event. A state emergency management agency that its own legislators call underprepared. A federal backstop that may not exist in its current form by the end of the year. And 326 years of accumulated stress instead of 15. The question Japan's example raises for the Pacific Northwest is not whether the earthquake is coming. FEMA, USGS, Dogami, Oregon, EM. They are unanimous. It is coming. The question is whether the 15 to 35 minutes between the earthquake and the first tsunami wave on the Oregon coast will be spent in an infrastructure built like Japan's, or in one that still alerts only the people who remembered to sign up. Part 11. What a prepared population actually looks like. Let me describe what happened in northeastern Japan in the 50 seconds after 4:53 p.m. on April 20th. The Japan Meteorological Agency's seismic network detected the earthquake's P waves, the fast-moving, lower-energy waves that arrive before the destructive shaking. Within seconds, automated systems were already calculating the estimated magnitude and epicenter. Emergency alerts were transmitted to cell phones across the affected region before the S waves. The slow, destructive waves had fully arrived at the coast. People in Iwate, Aomori, and Hokkaido received warnings on their phones with instructions to move to high ground. Television broadcasts interrupted. The public address systems in coastal communities activated. 175,957 people evacuated, orderly, to pre-established destinations on pre-established routes. The evacuation orders were issued to 82,811 households across 13 cities, 21 towns, and 6 villages. These are not numbers that reflect panic. They reflect preparation. People who knew where to go because they had practiced going there. That is what a prepared population looks like. Now let me describe what the July 2025 test event revealed about the Pacific Northwest. A significant earthquake off the Russian coast triggered a tsunami warning on the Oregon coast, where the Oregon Department of Emergency Management activated its alert system. Emergency alerts went out to people who had pre-registered with OR Alert, the state's opt-in notification system. People who were visiting coastal communities from out of town who hadn't registered received no alert. Representative Gomberg described sitting at dinner with friends from out of town during the warning. His friends got nothing. There were no follow-up alerts, no information about timeline for potential wave impact, no guidance on wave heights, no instructions for people encountering debris in the water. Oregon Representative Paul Evans' response: bring a $300 million preparedness package to the 2026 legislature. Create 6 to 7 new emergency responder training facilities over the next decade. Build a disaster recovery authority in the governor's office. Improve the notification system so alerts reach every phone in the impact zone regardless of prior registration. That package is in process. The legislature is considering it. As of this recording, it has not been passed. Oregon's official preparedness guidance currently asks residents to maintain 2 weeks of supplies, not 72 hours, 2 weeks, because the state's own emergency managers know that Cascadia will cut road and infrastructure access for months, not days. The I-5 corridor would be significantly damaged. Coastal communities would be isolated. The routes inland would be congested with evacuees. Lincoln County Planning's Onno Husing. We will have islands. Here is the number that contextualizes all of this. Oregon has approximately 22,000 residents in coastal tsunami inundation zones. The first wave would arrive within 15 minutes of the earthquake in many locations, possibly faster. On foot, moving uphill, with no driving, because the roads may already be damaged and certainly congested. 15 minutes is enough time to reach high ground if you know exactly where you're going and you start moving immediately. Japan built the infrastructure to make that movement possible. The signage, the elevated roads, the towers, the drills, the practice routes, the warning that reaches every phone. The Pacific Northwest is building toward that, slowly, with a federal backstop that is being dismantled at the same time. The risk is being better understood. Part 12. The honest verdict. Let me take you back to where we started. Every news outlet covered the April 20th earthquake, and almost none of them covered the part that actually has scientists worried. Here is that part, assembled completely. A fault segment specifically flagged in post-2011 peer-reviewed literature as a region of elevated Coulomb stress produced a magnitude 6.5 on March 27 and a magnitude 7.7 3 weeks later. The Japan Meteorological Agency issued the subsequent earthquake advisory for the third time in 18 months on the same fault. The advisory covered 182 municipalities, tens of millions of people. It ran for exactly 7 days and was lifted at 5 p.m. on April the 27th. On the same day, it was lifted. A 6.2 struck Hokkaido. The damage was minor. The preparedness worked. The warning system functioned. Japan's investment in post-2011 infrastructure performed exactly as designed. 10 injuries, 80 centimetres of water. Then none of that resolves the underlying question. Whether the Iwate segment has fully released the stress it has been accumulating. Whether the 3 advisory activations in 18 months represent a system gradually releasing pressure, or a system redistributing it. Whether April 20th was the main event, or whether the sequence is not finished. Seismology cannot tell you today. The GPS data is still being processed. The aftershock sequence is still being monitored. The models are still being updated. The answer will come from the instruments, over weeks and months, not from a news cycle that moved on within 72 hours of the advisory being issued. And 9,000 kilometers away, the Cascadia subduction zone is locked, has been locked since January 1700, as the Juan de Fuca plate is subducting beneath the North American plate at 4 to 5 centimeters per year. Stress accumulating, interface locked, no major release in 326 years. The Oregon coast has 22,000 people in the inundation zone. The alert system still doesn't reach everyone. The preparedness package is still being debated. FEMA may not exist in its current form by December. The I-5 corridor will be devastated when the rupture comes. The first wave arrives in 15 minutes. Japan showed the world what you can build in 15 years after a catastrophe. The Pacific Northwest has the opportunity to build it before. What April 20th revealed is not just about Japan. It is a working demonstration of everything that seismologists know about subduction zone fault systems, expressed in real time, on a fault that is in active conversation with the scientific community through its seismometers and its GPS, and its aftershock sequences. That conversation is ongoing. The fault is still talking. The question has always been whether we are listening. Part 13. Final frame. Let me take you back to where we started. Every news outlet covered this earthquake. Almost none of them covered the part that actually has scientists worried. The news told you about the waves, the evacuations, the advisory, the 1% figure, the no major damage. And then the news cycle moved on. Because that is what news cycles do. They process events. And when the event produces no catastrophe, when the waves are small and the buildings stand, the story ends. But the fault doesn't know the news cycle ended. The Iwate segment is still there, 100 kilometers offshore, at 20 kilometers depth, on a plate boundary that has been moving for millions of years and will keep moving regardless of what the Japan Times publishes or what advisory the JMA issues, or whether the world's cameras are pointed at it. That segment produced 3 events across 3 advisory windows in 18 months. The scientific literature said to watch it. It delivered. And the question of whether it is finished, or whether it transferred stress northward toward Hokkaido or southward toward the segments that ruptured in 2011, is being answered right now in data that will take months to fully interpret. The seawalls stand on the Sanriku coast, grey concrete, 15 meters tall, built from the memory of what the water did in 2011 and in 1896 and in 869. The stone markers set by survivors of previous tsunamis and telling those who came after, do not build below this line. Japan built the seawalls because Japan remembered. In Oregon, the evacuation routes are marked. The drill has happened. The 2-week supply recommendation has been issued. The $300 million preparedness bill is pending. A lawmaker who has been fighting for years is calling 2026 the last stand. And the fault of the Pacific Northwest coast has not ruptured since 1700, has produced no cultural memory of inundation in any living generation, has no stone markers, has no concrete walls on the coast. 326 years of accumulated stress, building, quietly, as it has been building for 3 centuries. Japan is showing the world right now what a fault system looks like in an active period, what the science looks like when it is confirmed by events, or what preparedness looks like when it is tested by an 80-centimeter wave instead of a 50-meter one. The advisory expired, the cameras left, but the fault is still there, and it has been talking for 15 years. The only question is whether we're listening.